Today, let me start by note on the fourth midterm examination that's gonna come on this coming Sunday. It should be at room 2102 and from 6 p.m. to 9 p.m. Prepare for it. Okay, that's gonna be 2.5 hours, and the problem gonna be two problem: approximate analysis, the frame subjected to vertical load, and another one, the frame subjected to horizontal load. And then we have another problem on the matrix displacement methods for the task. Now, let me move you to the final examination. We have only one more chapter, but it's going to separate into two portions. One going to be the beam, another one going to be the frame. And before I start to that point, let me take you back to the concept of analysis of the beam and the frame. We start our study with the slope deflection method. The slope deflection method is also the displacement method. In that method, we use the slope and the deflection as the unknown, and then we solve it. During the method, we got to make some important assumption based upon the slope deflection method. The deformation of the structure, that means beam and frame, mainly due to the bending moment, and then the behavior of the material during the bending is in the elastic region, and the deformation going to be very small. Then we got to understand this thing also for the matrix displacement method. We're going to use again the slope and the deflection, and also deflection in the x and y direction as the unknown. Then the derivation of the matrix displacement method, a lot of them can link back to the slope deflection method. And then after we derive all the K matrix, then we will assemble small k matrix into capital K matrix. And then based on the known force and this unknown force, we relate it to the capital K matrix in order to determine the unknown displacement. So we start with determine the unknown displacement of the beam and the frame first, and then later again we will determine the reaction, and at the end we will determine the internal forces and moment. And the method that we use is going to be the same for the task. However, there are some more detail about the small k matrix that different. So we will run quite the same procedure. However, there are some different things that I should note for the known force and moment. The task only subjected to the force, and then if you recall back, the force applied to the task at the node of the task. However, the beam is different. The beam, when it's subjected to the external loading, is subjected to the load between the node, not only at the node. That's going to be the main point. Then, based upon this one, the member of the task got to be the two force member. Again, coming to this one, the member of the beam will not be two force member. It's gonna bend. It's gonna subjected to shear force. Gonna subjected to the bending moment. And then after you get the small q matrix, that's going to be the internal forces, and internal bending moment, you can draw the free body diagram of the beam and the frame. And then you will use the own knowledge to draw shear force diagram, to draw bending moment diagram, to draw the elastic curve. So at the end, you will use your previous knowledge on the third learning objective to solve your final examination. And one more thing, I suppose you guys can use the computer program and then you can compare the result that you obtain from manual calculation with the solution from the software. Now, there are many examples of the frame and the beam. If you go to the F4 building, you will see this steel frame. If you walk Way, you will see this Academic 1 building. The Academic 1 building built by reinforced concrete, the steel frame, again, made by the frame. Mainly in our civil engineering, we gonna concentrate on the steel. So how about your steel design courses? It's supposed to be okay, right? Next term, you will study the RC1, reinforced concrete design 1, and later it's going to be reinforced concrete design 2 at the end of third year. Anyway, no matter the structure built by the concrete or built by the steel, one very important thing that Ajahn always asks you to practice drawing the elastic curve. What we did drawing the elastic curve is only for two-dimensional problem. However, in your real world, you're going to run the three-dimensional structural modeling, and then the elastic curve gonna be a bit more complicated, and that again is require the basic of your elastic curve drawing you have studied before. Now, Ajahn asked you already about practicing using the computer software, not only to structure, there are many others. Please have your free time and trying to use that program, compare the result with structure, compare the result with manual calculation. You will get better and better. Let me take you to the introduction of the analysis of beam and frame by using matrix displacement method. I said we're going to study the beam and the frame. However, due to beam is a subset of the frame, we will start with the frame. The first thing, talking about the global coordinate system. Again, typically in our study, I will provide to you. And when you know about global coordinate system, you will know the coordinate of the node. And then you're going to have the local coordinate system. And the local coordinate system for the beam and the frame going to be simple. For example, if you said you have this kind of local coordinate system, that means what? This means lambda sub x equal to 0, lambda sub y equal to 1. You don't need to do like the calculation for the inclined member. And this is going to help. Okay, I'm going to limit our study for the column in the vertical direction. And for the column in the vertical direction, there are two types of objects. One, upward, lambda sub x is 0, lambda sub y equal to 1. Downward, lambda sub x equal to 0, lambda sub y going to be minus 1. And then for the beam, such as this member, Ajahn always puts the local coordinate for the beam in this direction. Why? Because you're going to have lambda sub x equal to 1, lambda sub y equal to 0. This kind of setting going to help you in your final examination. But in the real world, the member of the frame may be inclined. That's going to be a lot of required manual calculation. But for this kind of setup, going to help you a lot. Then the nodal number, you're going to have the number with the circle. Member number, you just have the number with the square. the degree of freedom separate into two portions. One gonna be the constraint degree of freedom. This is going to be the degree of freedom at the support of the structure, such as this for the pin and this one for the fix. They are all zero if no differential settlement occur. And then you have another degree of freedom. You may call it free degree of freedom, or you may call it unconstrained degree of freedom. That's going to be the answer. That's going to be 1, 2, 1, 2, 3 over here. And then 4, 5, 6. And then noted on this one, 7. I always said, beware about the kid. Okay, it won't follow the X, Y, Z axis sometime, not the whole thing. Okay, not the whole time, sometime. That's going to be a lot of noted on this one. And then for the typical, you run X, Y, and Z. You run X, Y, and Z. Over here, you want the number will start by 7, 8, 9. Won't follow the same system. Now, after you separate the degree of freedom, again, you will come to determine Q sub K and Q sub U. Q sub U going to be the reaction, unknown, forces and moments. However, Q sub K for the frame got a different from the task. The task, the loading applied at the node. Then you can read the Q sub K immediately from the problem. But for the frame, also the beam, the forces may be applied between the nodes. Then you got to determine what so-called the fixed end moment and fixed end shear. Ajahn will provide you again with some equation for the fixed end moment. From the fixed end moment table, you should be able to determine the fixed end shear. Okay, we will talking about this one later. But the table that you use in the slope deflection equation, there are no fixed end shear. You got to determine it by yourself. Then that's going to be applied at the end of the member of the frame. Go back to the task. The Q sub K apply at the nodes of the structure. Then go to the third step. You got to reversing the direction of fixed end moment as fixed end shear that you obtain from the table. And then that's going to apply at the nodes of the structure. This is very important. Okay. And then you also require to determine the reaction. The fixed end moment, fixed end shear at the node also required to compute for the reactions. Okay, that's going to be the difference from the task. Then you determine the D sub K. That's going to be the degree of freedom 8, 9, 10, 11, 12. If there is no differential settlement, all of them going to be 0. That's going to be the same as the task. Then the small k matrix. We're going to have the small k matrix different from the task. Okay, sure, it's going to be different. Why? Because the task subjected to only the loading at the nodes. Okay, the task member is a two-force member. It's simple compared for the beam and the frame. Now, we will discuss about the small k matrix later. Again, the same concept will be used. You got to assemble small k matrix into the capital K matrix. Use the same method. Okay, and then you will get the capital K matrix. Then you determine the D sub U as you know on the task. Up until now, you're supposed to be pretty good on step number 6 and step number 7. However, when you determine Q sub U, the result of your matrix operation is not the answer. How come? Step number 3, you still have some fixed end moment, fixed end shear at the node. You got to use those in the computation for the reactions. Okay. There are some of them you use for the Q sub K, but there are the rest of them you got to use to determine the reaction. And then now you will able to determine the small q's matrix. Again, the way you determine the small q matrix for the task is going to be very easy. AEOL times the low matrix and times the capital D matrix. That's very simple. You get the result. If it's positive, it's tension. If it's compression, it's going to be negative. However, for this one, you got to put some matrix operation for the small q matrix of the beam and the column. Then when you get the small q matrix, not the end yet. If you recall, you still have fixed end moment and fixed end shear from the step number 3. That's you didn't use it. You just reversing it and apply from the end of the member to the node. Okay, then you got to put the fixed end shear and fixed end moment at the end of member. Apply it to the small q matrix. The result of that going to be used to draw the free body diagram of the member of the beam and the frame. Now, on step number 10, you're going to use the same knowledge and skill. Draw shear force diagram, draw bending moment diagram, draw the elastic curve. Okay, let us again review about global coordinate system that's going to relate capital Q matrix with the capital D matrix. Then most of the calculation from the beam and the frame didn't require much about the coordinate because as Ajahn mentioned, you got to know about lambda sub x and lambda sub y if you recognize this kind of local coordinate. Okay, and then this local coordinate got related small q matrix with the small d matrix. Local coordinate is gonna talking about the member. Global coordinate gonna talking about the structure, the beam and the frame, not the member. Then we will use the same concept. And one more thing, when we talking about the nodes, we got to talking about the support, the rigid joint. Mainly, it's going to be something like this. But actually, if you have the structure, for example, let me talking about the beam, and then you have the beam different with the moment of inertia. This one gonna be larger for the less, and then this beam member subjected to external loading. Then following what Ajahn said, you may say you have node number 1, node number 2, node number 3. This is not correct. Okay, most of the time, due to the change of this one, you got to say this is going to be node number 4. Okay, it's very important on this one. When you have the load applied at a point such as this one, and you also the immediate member section change, you cannot neglect it. You got to put it to be the node. Then this one, you will have member number 1, member number 2, and member number 3. Then in the final examination of the beam, Ajahn will focus on the beam. Only have 2 or 3 members, not more than 3. Okay, that's gonna help you. Also from the frame, I will have only 2 and 3 members. That's going to be the scope of our study. And then one more thing, the column go only in the vertical direction. It's not in the inclined direction. I think those kind of setup is going to help you a lot to reduce your calculation in your final examination. Then for something, if Ajahn said, okay, let Ajahn put something in different thing with the same beam, and if Ajahn said, let me put this one and put this one into the beam, how many nodes do you have for this second problem? Now the node will reduce to only 1, 2, and 3. The top beam gonna be easier than the bottom beam, and then for the top beam you will only have 1 and 2 member. That's gonna help you quite a bit. If Ajahn only check the support move kit into the point of changing of the section. Okay, now coming into the degree of freedom. Again, you got to determine the degree of freedom and the support first. But the number of them gonna be constant degree of freedom, gonna be the later. For the free constant degree of freedom, 1, 2, 3, 4, 5, 6, and 7 gonna come before 8, 9, 10, 11, and 12. Okay, and then the assumption of our analysis, as Ajahn mentioned before, the behavior of the structure gonna be linear elastic. The material used to build the structure gonna be isotopic and homogeneous materials such as the steel and small deformation. And one more thing, the deformation of the frame gonna due to bending moment and axial load. Take you back to the slope deflection equation. Ajahn tell you there is no axial deformation. Then when you draw the elastic curve, okay, the length of the beam and the column gonna be the same before the apply of the loading. But for this one word, okay, you will obtain the shortening of the column and also the shortening of the beam for the frame. So should be noted on that one. Now, the frame gonna have 3 degrees of freedom. That's gonna be degree of freedom in the x direction, in the y direction, and the rotation. That's gonna be about rotation of the slope and the v sub x linear displacement in x direction, linear displacement in y direction, and then you're gonna have the slope also. Moving to the beam. Okay, the beam has no horizontal force. The beam only subjected to the vertical load, and it can be at the point between the nodes, or it can apply directly to the node. And also sometimes is also subjected to the moment at the nodes. Whenever you have the moment applied directly at the node and the force applied directly at the node, you can use this immediately. However, when the beam subjected to the loading between the nodes, you got to determine fixed end moment and fixed end shear. Okay, and then you will use the fixed end moment, fixed end shear, use the third law of Newton, apply from the end of the member to the nodes. Okay, Q sub K, always taking at the node, not end of the moment. Okay, and then since there is no horizontal force, the deformation of the beam gonna occur only due to the bending moment, and then the degree of freedom of the beam going to have this kind of differential settlement and also the bending moment, and then you have only 2 degrees of freedom for the beam. It's going to be a bit different from the task. For the task, you have 1 and 2, that's for the task. But for the beam, you don't have horizontal. You have vertical and bending. However, for the frame, you have all of them, X, Y, and C. So this one, Ajahn won't use it. Okay, you can reduce the number of degree of freedom from 2 to 1 also if there is no settlement and no overhanging. But in this study, we will not. We will use 2 degree of freedom for unknown of the beam. Now, you may see for this one, the degree of freedom 1, 2, and 3. They're going to be the free degree of freedom or unconstrained degree of freedom. The value of this red degree of freedom gonna change when we check the magnitude of the loading. And then you will see we also have 4, 5, 6. That's gonna be constant degree of freedom. Okay, that's gonna be the settlement of the beam. Now, let Ajahn move you a bit to this very important thing. Again, the task, when we study about it, the task will subjected to the loading at the node. But the beam won't. The beam will subjected to the loading at the node sometimes, but most of the time it's going to be between the nodes. Then going back to the slope deflection equation, you will have equation to determine the fixed end moment. However, the table didn't provide you with the fixed end shear. You got to determine fixed end shear by using the free body diagram and equation of equilibrium. Now, fixed end moment and fixed end shear of this one apply at the end of the member, not the node. Okay, you got to use the third law of Newton. Transfer fixed end shear and fixed end moment apply to the node of the frame and the beam. This one will be used for Q sub K, and also we will use for Q sub U. Okay, and then on this one, you also will use it for small q matrix. Okay, at the step maybe number 8. Okay, so don't forget the obtain of the internal force and moment small q must be superimposed with the fixed end moment, fixed end shear on this one. Then on the task, Ajahn didn't mention anything about how the metric equation come from. Okay, and I think it's time for us to check how the metrics come from. Ajahn should start with this one. We have the local coordinate system. Local coordinate system gonna talking about the member of the beam and also member of the frame. Okay, and this one is in the local coordinate system. That means if we have the member, we will have this one in the x palm direction, and we have this one to the y palm direction. This is the coordinate for the member of the beam and the truss. Now, in the local coordinate system, we talking about the internal forces and moment and the internal deformation. What do we have for the internal forces and internal moment of the beam and the frame? In the, let me put it another color. In the engineering static, we have normal force, and then we have shear force, and then we have bending moment. The same concept uses over here. This is going to be the internal bending moment, and this is going to be the normal force, and then this is going to be the shear force at the near end, and this is going to be the shear force at the far end. This is going to be the normal force at the far end, and then you have another one. This is going to be the bending moment at the far end. Related to each other, this one are going to be axial deformation at the near end, and this one going to be axial deformation at the far end, and then this is going to be differential deformation, and this one also be the differential deformation, and this one going to be the slope, and this one also going to be the slope. Now we will consider them into three separate cases. One, due to the axial force. Second, due to the shear force. Third, due to the bending moment. And then we will get the K-palm matrix for each cases. For the axial force, that's going to be close to the task. But for the shear force and bending moment, it's going to be the new thing. Then we will have this one as the K-palm matrix related the what so-called member forces and moment to the member deformation. Now, start of this one. You're going to take this axial force at the near end. We assume the deformation occur here to be small axial deformation d sub n palm. Now, let Ajahn take you to our good old day. We have axial member subjected to the force P. Okay, then the stress occur here gonna be P over A. And then the strain occur here gonna be the deformation divided by the length L. Under the force P, we have this deformation. Then due to the linear elastic behavior, we have sigma equal to E epsilon. Then you will have the force, let's put it into the force here, P over A equal to E delta over L. Then following this one, the P, axial force, gonna be A E over L and then delta. And this is what? This is what we use to determine the small k matrix of the task. It is the axial stiffness of the member. This is called axial stiffness of the member. Then coming over here, due to this deformation, put this deformation over here. So the force here can be determined. Okay, if you use this one 1 millimeter times AE over L, you will know the force over here to be AE over L times the deformation. Then if you use the summation of x sub f palm equal to 0, since this one subjected to Q sub capital N x palm over here, you will have the resistance force. That's going to be Q capital F x palm. And then this is putting in this opposite to the positive x palm. Okay, this is in the positive x palm. The sign of them gonna be different. And then there is another thing. There is another way due to the deformation at the far end in the x palm direction. How this occur? There's gonna be the force, axial force over here. This axial force over here gonna be the stiffness times this deformation. So you determine the axial force at the far end and the x palm direction to be AE over L times the deformation. Then this end, we're going to have the opposite forces, and that's going to be AE over L, D sub F x palm. Okay, actually, if you consider only the near end, okay, you have two forces. That's gonna be this force and this force. And if you consider at the far end, the member gonna subject these two force. We can rearrange everything and put it into the matrix. You will get this one. Okay, for example, if you said about Q sub n Q sub n x palm, this is going to be equal to AE over L times what? This one times D sub n x palm, and then minus this term AE over L D sub, take this one times this one D sub F and X palm. You will see this term is going to be this one. No, it's going to be this one. Okay, this one. This term going to be this one. That's going to be positive. And this term, AE over L, D sub X going to be this one. And for Q sub X F palm, the first term going to be AE over L minus, and D sub n X palm going to be this one opposite to X palm, and then the last one of this term going to be this one. Anyway, after you put everything, you put it into the small k palm matrix, you get this one. Now, for the y palm displacement, Ajahn just said this only have the D sub n y palm. Again, if Ajahn said this is A, this is B, the moment over here is going to be M sub AB. From slope deflection equation, you will have 2EI over L, then 2 zeta A plus zeta B minus 3 times D sub n y palm over L, and then there is no loading plus fixed end moment AB. This is gonna be 0. Since there is only D sub n palm, this term is 0. This one also, this term is 0. So you will have 2 times 3 minus 6, and then EI and D sub n y palm, and then L square is going to be the moment occur over here. You will get the result to be 6 EI. Okay, and then L square D sub n y palm. The same thing, if you determine M sub BA, that's going to be 2 EI over L. 2 zeta B, no slope here, plus zeta A, no slope here, minus 3. Now, that's going to be D sub n y palm over L and plus 0. Now, you're going to get the moment over here to be the same. 2 times 3 is 6, and then EI divided by L square D sub n y. Okay, and then after you get this kind of deformation, Ajahn, how come negative? If you recall previously, in the slope deflection, this way is positive. So when it gets negative, you get this kind of rotation. Then you have this one, and this one, you have this one, and you have n shear. Okay, if you take the moment over here, summation moment about V equal to 0. This is going to be V sub A times the length L, rotate in this positive direction. Then it's going to be these two things. 6 EI over L square, 6 EI over L square. You will have this one, 12 EI over L square. d sub n y prime. Then you take this one out, put this one gonna be L cube. Okay. Then you get the coefficient of the K prime matrix. And then do the same for this one. You will get the same result. Thinking about the professor 60 years ago, they're trying to solve the equation to obtain the matrix. That's going to be based on slope deflection equation. Now, we have one more. That's going to be the slope. The same basic thing. This is going to be A. You got to determine the moment over here. M sub AB. Gonna be 2EI over L again. The slope over here 2D sub N Z part. And then plus slope here is 0 minus 0. No differential settlement. And then fixed end moment gonna be 0. No loading. So M sub AB gonna be equal to 4EI over L. D sub N Z prime. You will have the slope over here. And that's gonna be 4EI over L, d sub n sub prime. And if you recall over here, it's gonna be M sub BA. That's gonna be 2EI over L. And then 2 theta sub B 0. And then d sub n z prime, the slope over here. And then minus 0 plus 0. Then M sub BA gonna be half of the M sub AB. That's going to be what? As we obtain from this one, M sub BA. This is going to be half of this one. The same that we derive in the moment distribution. If you have the moment at this one, hint, and this one fixed M sub AB, going to be 2 times of the M sub BA. And then do the same thing of this one. Rearrange, determine the end here. And then do the same of this one. You will get this one. After you combine all of them together, you will get the K prime matrix. Again, that's got related to the force and the moment at the end of the member due to the deformation at the end of the member. It's not for the structure yet. Okay. Now, you got to relate this thing from the member to the structure. Okay. Ajahn, how come you trying to solve this? Actually, Ajahn would like you, if, for example, you go to study in the US and then the professor that you study with asks you about this. And you said, Ajahn, the professor, my Ajahn in Thailand didn't teach me at all about this one. That's not a bad thing. Okay. I'm going to do my duty. Okay. Explain you how the small K matrix come. This is only the K prime matrix, not finished yet. Okay. Now, to obtain the K matrix, we got to do more consideration on what? On the relationship between the local coordinate x prime y prime with the global coordinate x and y. How to relate it? Go back to the subject of engineering statistics. At the time when you are younger than this for a year, your age also, if you are 18 now, that means during your 17, okay, this is going to be positive x, positive y, and positive z. Then there is the force vector or maybe the position vector. In the engineering statistics, we define the angle here to be alpha. We define the angle here to be beta. And then we define the angle here to be gamma. The problem that we discuss is in 3 dimensions. However, our problem is only in x and y direction. So, if Ajahn make it more simple, Ajahn only put this vector in the positive x and then in the positive y, and อาจารย์ change this one for the alpha to zeta sub x, for the beta to zeta sub y. Now, as you may project it over here, okay, what you have over here, you may flip it up, and then the local coordinate here at this point x n y n, and at this point it's going to be x f y f. Now let Ajahn put it into these pictures. It's going to be easier. You can determine the length from here to here. That's going to be x sub f, this one, minus x sub n. For example, if this is 0, 0, this is going to be 4 and 3. This one going to be 4 minus 0. 4 minus 0 is going to be 4 meter. And if you interested in this one, it's going to be y sub f and then minus y sub n. From this one, this is going to be 3 minus 0. 0. That's going to be 3 meter. Now, the length of this one. The length of this one going to be square root of what? X sub f minus f sub n square plus y sub f minus y sub n square. It's going to be square root of 4 square plus 3 square. And this is going to be square root of 25. And that's going to be 5 meter. Okay. Now, we are looking for cosine zeta sub x. To determine cosine zeta sub x, you got to have x sub f minus x sub n and then divide by the L. In the computer program, you will get this equation. And then for zeta sub y, you got to come to this distance. Okay, and then it's going to be y sub f minus y sub m, y sub n, the green, divide by the red. This is going to be the green, and divide by the red. You get this equation also. Is these two equations for sure going to require for the task. However, for the beam and the frame, don't worry. Okay, you can leave it for the scope, as Ajahn mentioned. But if your frame have inclined member, you're going to have a tough work. I will show you later. Now, after you know about the direction cosine of the frame member, we come to determine the what's so called capital T matrix. Capital T matrix is the displacement transformation matrix. It's going to relate the small d with the capital D matrix. Now, we assume there is the deflection occur on the frame, capital D and X. And this capital D and X can be separated into these two components. The component over here is going to be D sub nx, and this angle cosine zeta sub x. And then since you have this for cosine zeta sub x, this one will be capital D nx cosine zeta sub y. Do the same for this capital D sub ny, project it to determine the relationship to the small d. Okay, so this is going to be this one going to be capital D ny cosine zeta sub y. This one cosine zeta sub y, and for this one is going to be capital D ny cosine zeta sub x. Now you do the same for the c-axis. However, the c-axis is going to be the rotation. Okay, the rotation of the member and rotation of the frame. they are for the z-axis, the same axis, just only in the z-axis, they are equal. Then for the far end, you may do the same thing, and then you arrange all the coefficient. Then you get the capital T matrix. This called displacement transformation matrix. Okay, if you prefer to study structural engineering for your master degree, you cannot escape from this one. Okay, there are courses asking you to write a computer program to determine all these things. Now, there is another thing that's related to this one. This is small d with capital D. Then come to the next one. Small q with the capital Q. This is going to be external forces and moment. This is going to be internal forces and moment. Starting with the internal axial force, you can project it. This one, zeta sub x q sub nx prime cosine zeta sub x in the y direction, you get cosine zeta sub y. And then for this one, you still project the small q matrix for the member into the structure q matrix. Okay, this one gonna be q sub ny prime cosine zeta negative because it's opposite to the x. And then this one is going to be q sub ny prime cosine zeta sub x. You do all of these things again and rearrange everything. What do you get? It's going to be capital T transport matrix. Ajahn Chu said there is the transport over here. What the meaning of transport? Okay, Ajahn will talking about this one over here, passing over here. For the transport matrix, you will see this column going to be the same of this one. This going to be the transport of T into T transport. For this one, when you transport low, going to be the column. And then this low gonna be this column, and then this low going to be this column, and then this low gonna be this column. Transpose means you switching between low and the column of the matrix. Now, for derivation of small k matrix, you got to do some matrix operation. We're starting over here. Then we determine the displacement transformation matrix. Put this one over here. You will get this matrix. Ajahn Chu said this is very important one. You will use this small q equal to k prime, capital T matrix, capital D matrix in order to determine internal force and internal moment of the beam and frame member. We will use that later. And then we have the force transformation matrix. Just take this one over here. You will have the equation over here. Then the multiplication of capital T transport matrix with the K prime matrix with the T matrix transformation matrix gonna be small k. Then you go to this one. You got to do multiplication of this all three matrix. You got to require a lot of matrix manipulation in the form of symbolic analysis. Luckily today, you may have the computer program such as MATLAB, okay, or so you may have MATCAD, okay. Those kind of computer program can do matrix manipulation based on symbolic analysis, Mathematica also. And then at the end, you multiply them, you get this one as the answer. Related to capital Q, and then to the capital D. This is the same form as the small k matrix when we talking about the task. However, there are a lot more complicated. Don't worry, Ajahn will provide this one for you. In the final exam, you will have the equation, the matrix equation for a page. Okay, this is going to be part of the small k matrix. I also provide you the k-palm matrix. I also provide you the transformation matrix. Okay, that's required you to do the computation. Now, when Ajahn talking about the member in the vertical direction, such as this one, if you have this one, lambda sub x equal to 0, lambda sub y equal to 1. Then when this one occur, any term that have this kind of lambda sub x, lambda sub y will be 0. That's going to help, right? The same thing. If Ajahn put the member in the horizontal direction, lambda sub x equal to 1, lambda sub y equal to 0, all of this kind of multiplication of lambda sub x and lambda sub y going to be 0. All of this term going to be 0. And now, you got to be able to reduce from the small k matrix of the frame to be the small k matrix of the beam. The beam one node have only y and z axis. Then there is no axial deformation near end and also the far end. Okay, when you eliminate the row, you got to eliminate the column. Okay, for the beam, lambda sub x equal to 1, lambda sub y equal to 0. So this term gone. This term change to 1, change to 1. This term change to 1. So the important coefficient for the beam gonna be 1, 2, and 3. Okay, and then also you have this one really easy. This one is 4. Only 4 coefficient important. Let's simplify this one to this matrix. Now, this is going to be small k matrix. That's you're going to derive it by yourself. Okay, and then actually there are some guide the same way that we did for the task. Separate them into 4 partitions. Okay, and then take the first partition, compute this one, compute this one, compute this one, and then make a copy of this one to over here. So you get the first partition. You copy everything from the first partition, this one, this one, this one, and this one, and then you apply negative over here and negative over here. Okay, there are different between 1, 1 and 2, 2, only for the negative. Then the same thing occur. Just make a copy of this one, and this one, and take this one, divide it by half, and then put negative, negative. And then do the same. Just take negative here, copy this one over 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 here. Okay, just trying to do it by yourself. Okay, you will use toolkit, and this one won't be just tough. Now, this second method I can skip. It's going to get the same result of this one. And for the overhanging beam and no settlement, sometimes you may reduce the vertical deformation, and then small k matrix is going to be easy, but we won't consider this one in our study. And now, taking all of this one, we will move this one. We will move to assemble of the small k matrix into the capital K matrix. Anyway, อาจารย์ ask you at this point did you practice some for the task if you do this some practice for the task you're going to use that skill for the beam and the frame the same skill okay the detail of this one can be show you over here the same way we have small k1 matrix and small k2 matrix small k1 matrix has the degree of freedom 1, 2, 3, 4, and then 6, 5. We start with row number 1. Copy 177.78 over here, row number 1. And then copy 0 over here. Copy this number over here. Copy this number minus 1777.78 over here. And then 6, that's gonna be this one. And then 5 over here, 2666.67. And then do the same for the row number 2. Start with 1, 2, 3, 4, and then 6. This is 6 over here, and then 5. Row number 3, 1, 2, 3, 4, and then 6, and then 5. Noted on this one. And then row number 4 over here. Start 1, 2, 3, 4, 6, and then 5. And then the last, no, that's not 6. Okay, row number 6, right? Row 6 over here. 1, 2, 3, 4, 6, and then 5. The last one, row number 5. 1, 1, 2, 3, 4, and then 6, and then 5. Okay. And then the second one going to be easier. Okay. Row number 1, 1, 2, 3. Row number 1, 7, 8, 9. Row number 2, the same. Row number 3, the same. Then jump to row number 7, 1, 2, 3. 7, 8, 9. Row number 8. Row number 9. Okay. Again, in the final examination, the beam, you have 2 or 3 small k. The frame, that's for sure, 2 or 3. Okay, just put it. But for the task, you may get more. Okay, task is going to be easier. Then do the same calculation as before. Okay, separate the capital K matrix into K11, K12, K21, and then K22. And then Q sub K equal to K11 D sub U plus K12 D sub K. Following the same as we did, okay, UK have Q sub U equal to K21 D sub U plus K22 D sub K. Okay, do the same calculation as before. Going back, trying to do the matrix manipulation for this PowerPoint. Okay, use your calculator first. Okay, practice it. Don't make any mistake for only one member. If you cannot inverse the matrix, that means your matrix is not symmetry. You go back and check the symmetry of the matrix. Then, most of the time for the problem on the frame, Ajahn will have no differential settlement. But take note on the beam. Sometimes Ajahn provide settlement. Then this one gonna be easily to determine D sub U gonna be the inverse of K11 times D times Q sub K. When you get D sub U, put D sub U over here. This term is 0. You can determine the reaction. Again, the reaction now is not the answer, not the task. For the task, you can answer immediately. But for Q sub U, you got to take this Q sub U with the fixed end shear and fixed end moment. Okay, applied at the node. Okay, and then coming to the beam, let Ajahn start the calculation. For the beam, again, Ajahn will put the global coordinate system the same on the same. The origin gonna be on the left. then the local coordinate gonna be in this direction. Lambda sub x equal to 1. Lambda sub y gonna be 0. Okay, node number, member number, degree of freedom. Now, let's check. You will have, this is going to be free degree of freedom since it is lower. This is going to be free degree of freedom. How about this one? Fixed. Okay, so no, it's going to change to the blue. You have only two unconstrained degree of freedom for this problem. Only two. Okay, and then the number going to be the red, come before the blue. You may say this can be number 1, this is number 2, and then this gonna be number 3, number 4, number 5, number 6, something like this one. Ajahn will provide everything for you, but you should be able to separate degree of freedom into two sets. Okay, free degree of freedom, paint it with pink. Unconstrained degree of freedom at the support, paint it with light blue, something like that. And the number of pink come before the light blue. And then determine the fixed end moment, fixed end shear. This is going to apply at the end of the member. You cannot use it. You only use this one for small q matrix later. You got to reverse, okay, the direction. However, before going to that point, again, fixed end moment didn't come with the fixed end shear. For the symmetry, the fixed end shear gonna be easy. How easy is it? Separate them into half. Okay. However, when you get, okay, this one also separate to half due to the symmetry. However, for this one, the fixed end shear at A won't equal to fixed end shear at B. Okay, you got to be able to determine. You don't have the equation. You will have this equation, and then you calculate them to be a number. Use the free body diagram to determine the fixed end shear with the equation of equilibrium. Okay, so all this one, I assign you guys go back and try to determine the fixed end shear from the fixed end moment by provide the given value over here. Now, all of this apply at the end of the member. You got to determine Q sub k by reversing the obtained fixed end moment, fixed end shear at the end to apply at the node. And then you will have capital K, capital Q sub k. And part of them will be used to determine capital Q sub u, the reactions. And then D sub k going to be straightforward. Nothing much different. For the small k matrix, again, read the degree of freedom and do the same as Ajahn mentioned. Only 4 member required for the determination. You have this one. You got to simplify them and take part of this member, this member, this member, and this member out. Put it in your calculator. You're going to be in the form of number. Okay, and then again, just copy this one over here. Now, you get the first partition. On the last partition, just put this negative. Okay, on this partition, just put this one and put this one. Copy this 1, 2, 3 over here. The same over here. If you get this one, copy them over here. You have only one page. Okay, be careful to use the reduction. You should put it in the separate page and you get the result. Now, you have this one. Okay, again, combine small k matrix into capital K matrix as before. And then do the computation with your calculator. And then when you get the Q sub u, don't forget to take this one from the step number 1, from the step number 2 from the step over here, combine with small q, and then you will get the free body diagram of your structure. And then after you calculate to the small q matrix, you will draw the free body diagram of your members, not structure, not the beam, member of the beam, and then draw the shear force diagram and draw the bending moment diagram. And again, you got to be very careful during this calculation. For the frame, you got to calculate this one. But for the member of the beam, since this matrix is going to be what's so-called identity matrix, then for the beam, you can take small k matrix from your step number 4 and put it into step number 9. Compute for the small q matrix in order to draw the free body diagram of the beam's member. And now, on the step number 10, you're going to do the same as you did in the slope deflection in the moment distribution. Okay, draw shear force diagram, bending moment diagram, and elastic curve. And I should note that elastic curve of the frame in this chapter a bit different from the elastic curve of the frame in the slope deflection, because at that point we do not consider the axial deformation, but this one we will. And then it's going to be only one more example. And before I start this one, let me stop recording on this one. Okay, let me start our second session, and we have the beam in this example, and it's going to take only 10 minutes, not more than that. Starting on this one, this is an example. Ajahn will provide you with all the required about global coordinate system, local coordinate system. If you follow this one, even though Ajahn won't provide you with the global coordinate system, let you know that this is going to be x and this is going to be y. Actually, in beam, on our scope, you don't need to determine the coordinate. Okay, you have practices for the task already. Now, this is going to provide you with the local coordinate system, and you're going to get the same node number and also the same member number. For somehow, if Ajahn just skip the number of the degree of freedom like this one, Ajahn would like you to know that degree of freedom separate into constant degree of freedom, and you should be know that this is constraint fixed end, this is constraint, okay, this is constraint roller, and this is constraint, and this is constraint. There is only one free or unconstrained degree of freedom. This is going to be 1. If Ajahn said this is 1, okay, this is 3, this is 5, so this one supposed to be 2. This one supposed to be 3, y before, and this one gonna be 4, c, okay, and then y, this one 5, and then this one 6, fill the blank. Okay, you're going to have the same number. Ajahn force you, but if you make a mistake on this one, your calculation gonna be weird. Okay, when you stretch. Now, after this one, the EI gonna be constant. Sometimes Ajahn provide you with the EI with the number. Sometimes Ajahn won't just be in the form of EI. If Ajahn said This is the symbolic analysis. The end of your D sub capital D sub U gonna be dy by EI. For the task, it's gonna be dy by AE. Okay, this problem, your capital D sub U gonna dy by EI because we don't have the value EI yet. Now, following the global coordinate system, local coordinate member number, degree of freedom, we start our calculation. On the second step, you got to determine fixed end moment, fixed end shear at the end of the member. Again, follow this one. Follow this member. You will have fixed end moment, fixed end shear. However, member number 2, you don't have it. Okay, then you can determine fixed end moment. This is gonna be WL square over 12. Okay, you put it in your calculator, and then this WL square over 12 or 75 kilonewton meter, one applied node number 1, you don't use it yet, but another one applied node number 2 on this node number 2 relate to capital Q1. You got to use the third law of Newton, transfer 75 kilonewton meter over here. And then there is fixed end shear. This is WL over 2, 25 times 6 over 2. That's going to be 75. You don't need it yet because there is no free degree of freedom related to the shear. Okay, so this problem going to be only this rotate clockwise, the result rotate counterclockwise, and it is in the direction of degree of freedom number 1. So capital Q1 gonna be plus 75 kilonewton meter. Okay. Ajahn, how about the author? Don't worry. This 75 is going to be this one. We will use this later. On this node number 1 over here, you also gonna have this 75 kilonewton, and also you will have this 75 kilonewton meter, but you will use them when you determine capital Q sub U, not this one. Okay, now after you have this one, and you may say, Ajahn, capital Q sub U bases upon this one, you will have what? You will have all requirement of capital Q2, capital Q3, capital Q4, capital Q5, capital Q6, capital Q7. Okay, and then this one related to capital Q sub U minus upward positive, downward minus 75 kilonewton. And how about 3 over here? This is going to be minus 75 kilonewton. And then this rotation produce this kind of rotation. See, opposite to degree of freedom number 2, but it's going to be 75 kilonewton meter. So keep this one as your capital Q sub U. Okay, and we will determine all of this reaction later. Taking capital D sub K, no settlement. All of them gonna be 0. If Ajahn Cheng putting this one to be 10 millimeter, okay, putting this one upward to be 10 millimeter, thing gonna change. Okay, so for this one is in number 2. This one change to minus 0.010. This one in number 5, this one will plus 0.010 meter and meter. See, negative downward, positive, upward, can be, and then let อาจารย์ take you back or going to be zero. Now, what we have is going to be small k matrix. Only 4 members of them are required. Number 1, number 2, number 3, and number 4. After you get number 2, you get this one. So copy 1, 2, 3, 4, and then change the sign. Okay, and then copy only 1, 2, 3, put the sign, and then copy 1, 2, 3, put the sign. That's it. Then coming to the member number 1, degree of freedom gonna be what? Near end and far end is gonna be 3, 4, 3, 4, 2, 1. Okay, it's gonna be 3, 4, 2, 1. Very strange, อาจารย์ don't worry. YC, YZ, YZ. Okay, X, YZ, 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 and then put everything. Now, EI gonna be over here. You have no number. You got to have EI. And then for member number 2, do the same thing. You have degree of freedom gonna be what? This is near end. This is far end. 2, 1. 2, 1. And then 5, 6. Taking 2, 1. 5, 6. Do the same. Putting the coefficient together. Taking the EI. Then you got to assemble small k1 and small k2 matrix into the capital K. Putting them together. Then start with number 3. Okay, with what? Taking this one 3, 3. Taking this one 3, 4. Wrong, อาจารย์ Yes, I'm wrong. That is not correct. Okay, you got to start a correct one. 3, 3. Okay, and then 3, 4, and then 3, 2, and then 3, 1. Beware about it. Okay, EI, and then 3, 3, 3, 4, 3, 2, and 1. Coming state to number 4. Number 4. Number 4. Start here. 3, 3, 4. This one. 4. And then what? 2. Over here. Over here. 2. And then 1. And then jump to what? Number 2. On top. 3. And then 4. And then 2. And then 1. Jump to the last one. Lower one. 3, 2. And then 2, 1. Okay. And the next one, do the same. Row number 2 is over here. Row number 2. Row number 2. Start with 2. Row number 2. Start with 2. And then 1. 2, 1. And then simple. 5, 6. 5, 6. Then go to row number 1. Row 1. And then start with 2. So 2 here. 2. And then 1. 2, 1. And then 5. And then 0.25, 6. And then row number 5 over here. Start with 2, 1, 5, 6. Row number 6. Start with 2, 1. And then 5. And then 6. Combine them together. And then beware about EI over here. Okay. Then you will see 75 equal to EI. You will have 75 equal to EI. And then this matrix is going to be 1.6667, this one, and times D1, and then plus 0. This one equal to this one times this one. This one times this one going to be 0. Then you have this one very simple. Take D1, inverse this one. Okay, just inverse this one, inverse this one. Very easy. So EI gonna be divided. Every problem that has no value of EI, no value of EA, you got to divide the answer by EI or EA. Okay, now take it back to determine this reaction. So, this one positive. When it's positive, it's gonna be X, Y, and C. It's gonna be counterclockwise. So the rotation over here, gonna follow degree of freedom number one. This is going to be the rotation. If you know this kind of rotation, for sure, you may sketch should have this inflection point. Now, putting into this reaction is going to be equal to EI of this term times D1. And you can see for this one, EI will eliminate each other. No matter the value of EI, the reaction won't care about the EI. Okay, and then when you get it, don't forget about the result that we did before. Minus 75 kilonewton, minus 75 kilonewton, minus 75 kilonewton meter. Okay, and take it over here. Then the real reaction will obtain. Then you got to write for the reaction. What's going to be Q2? This is positive. Q3, positive, upward. Okay. Q5 gonna be negative. All of this gonna be reaction force. However, we will have Q4. Where is Q4? Over here. And we will have Q6. These two gonna be the moment. Okay, that's gonna be the moment. You will draw this one. Then you may check for the equilibrium. The problem must be in equilibrium. If not, go back to step number one. Recheck everything. Okay, check everything. You got to be in equilibrium. If not, you don't need to go further if this is wrong. If you still working concrete, it's going to make the answer wrong. Okay, so taking the equilibrium. Then at this point, small q gonna be K palm transformation matrix and capital D for the beam. I just said only for the beam. The beam that we have in this direction, lambda sub x equal to 1, lambda sub y equal to 0. This transformation matrix going to be identity matrix. Then the result of this one going to be small k matrix that we have on the step number 4, if I'm correct. Okay, take back to step number 4. Take this one. And you know this gonna be 3, 4, 2, 1. Capital D3, capital D4, capital D2. All of them 0. And this one, capital D1. And then EI, eliminate EI. This gonna be the internal force for the member number 1, force and moments. Okay, now you have this one. And then the second one, do the same thing. Take this one from the step number 4, and then 2, 1, D2, D1, and then D5, D6. And then do the same calculation. Now, don't forget about the degree of freedom that we have, and then translate it. This one corresponding to number 3. And then Ajahn Fu said, don't forget about fixed end moment and fixed end shear at end of the member. This one from step number 2. We didn't do it yet because on the step number 2, we reversing it and use it in step number 3 for capital Q sub K. And important thing, this is 10.716. This is in this direction. So this is going to be the force 10.716. This is going to be minus of this one. And then this is going to be the moment and positive. That's going to be rotate in this direction and rotate in this direction. You can see rotate in this and rotate in this direction. Now, clear everything. Coming to the second member, put it over here. Okay, and this is positive. That's gonna be in this direction. This is negative in opposite direction, up and down. And then you have the bending 32.143. That's gonna be in this direction. Okay, the same direction, counterclockwise. And this one also counterclockwise. Now, you got to combine them. Okay, get the result. The result of this one gonna be this one. Take 75 kilonewton and 10.716. You get 85.716. Then this is counterclockwise. This is counterclockwise. Combine them, you get this 94.428 counterclockwise. Then 75 upward. This one is downward. Minus 75 minus 72.856. Okay. Oops, not yet. You have this one. And oh, I'm wrong. Ajahn wrong. This is 75 and this one 10.716. This one here. Okay, you get this one. And then the moment over here, 75 clockwise. This is going to be counterclockwise minus 6. Okay, minus 6. And then coming over here, just copy them. This is what? This is 6.027. And this is going to be 0 and 32.143. Just copy it. And then just copy this one and copy 16 point. Now, you only use this free body diagram and use this free body diagram. You have both end shear and end moment. You can draw the shear diagram, moment diagram, and elastic curve, and also put the inflection point. This is going to be what you're going to practice. And I said, please use at least 5 significant figures in our calculation. Okay, that's going to be the end of this lecture. Number 18. Any question? If no question, next lecture we will work together on the extra example. We have 2 more. Okay, and after finish the beam, we will move to the frame later. Okay, have a good day. Bye bye.